Ladies and gentlemen, welcome to lecture number 16. So in this lecture, we will continue with linear approximation and differentials. Well, as you have seen last time, we talked about some stuff regarding linear approximation and differentials. And this time, I would like to continue with more applications. So let's continue. And in fact, with this lecture, we will finish the chapter. So last time we had this propagation, right, error, and we wanted to see if it was large or small. So like I said, this will be the last lecture for this chapter. In this way we will finish the first 3 chapters, and then next week we will start chapter 4, which will be devoted to qualitative properties of differentiable functions. You will see more about, anyway, I'm not going to go too much into detail about what we're going to talk about next week, but you will see something that's really nice about differentiable functions. And let me tell you one thing, the material will get much more complicated than it is at this point. So starting chapter 4 and chapter 5. So those will be the last 2 chapters and to finish up the course. Okay, now let's see another application. So let me read this problem. And you see, it says the following: the crew of pigs in space discover a giant cube floating in space. Their sensors report that the size of the cube are 4 meters long, but they know from several previous unfortunate incidents that their sensors are only accurate within 2%. What is the error and the percentage error in their measurement of the volume of the cube? So when we have such a problem, we need to identify, what we're dealing with. So we have a giant cube, so the word cube here, floating in space. And we know that the sides of the cube are 400 meters long. So that's another information. But they know from several previous unfortunate incidents that their sensors can only accurate within 2%. Okay, so we're interested in the measurement of the volume of the cube. First of all, I'd like to ask you, what is the volume of a cube, right? So what is a cube? Let's draw a cube here. Look, a cube. So a cube is something like this. Something that looks like this. Okay, so that's a cube. All the side lengths are equal. Let's say all of them are x. Everything is x. Right? And I'm asking you, what is the volume of the cube? So let's say the volume of the cube is what? Can you tell me? Exactly, it's x cubed. All right, so that's the, and by the way here, you see x will vary. So we will have that v of x, and let me be more specific here. So this guy is a function of x, so it's v of x, right? Which is x cubed, so. All right, so what should we do first? Since we're asking about the error percentage of the cube, of the volume of the cube, maybe we should take the derivative of the cube, right? So again, the function v of x is x cubed. And if we take the derivative with respect to x, so here dv, when I say dv, I mean dv over dx. So let me be more specific here. So v of x is x cubed, just like we said. And here dv is nothing else than the derivative with respect to x. So this guy is dv over dx. Or if you want, v prime of x, right? And v prime of x is nothing else than just 3x squared that you see here. Look at this here, right? So this guy here, right? Or if you want, we can write it in terms of the differential. This is dv. Okay, let me write it like this. So this guy is v prime of x. But if we want this in terms of the differential, dv will be 3x squared dx. And now we know who x is. We said that it's 400 meters long, right? The size of the cube, right? Look here. We have this information here. Are 400 meters long, so we're going to replace x by 400, right? And we know that dx, right? You see, that's the thing, that this is the tricky part, I would say. We know that that their sensors only accurate within 2%. So it is, so this guy here, well, because of this information, right? This guy will be dx. So this thing here is dx. And now by just doing algebra, this will give you 3,840,000 meters cubed, right? 348, anyway, 384, sorry. And now the percentage error, you just need to multiply by, you divide by v and you just multiply by 100. So this will be 384,000 over 400 cubed times 100, which will give us 6%. So that's the percentage error, right? Or you can also do an alternative method. You can just use directly this formula. So for the percentage error, right, you can use dv over v. And you know that dv is this guy, so, right, this guy here is dv. This guy here is v. And then you just, at the end, will give you 3 times dx over x. And you know that this is 3 times 2%, because this is 2% here, which is 6% at the end of the day. So as you can see, these are the same thing, right? All right, now let's see another problem. And I want you to think of this for a bit. So a sphere is measured to have radius 21 centimeters. If the radius is increased by 1%, how much does the volume change? And also, what is the percentage error in their measurement of the volume of the cube? So pay attention here. Well, the volume of the cube, I think it's a mistake here. I think it's the volume of the sphere, I'm sorry. Anyway. So let's think a bit for a couple of minutes. So let's identify here. So what are we dealing with? So we're dealing with a sphere, and we know that the radius of the sphere, so let's identify the keywords here. So a sphere, so, and we know that the radius is 21 centimeters. So we know that, let's say R is 21. Okay. If the radius of pay attention is increased by 1%, so it's by 0.001, then how much does the volume change? So we're dealing with the volume here. So once we deal with the volume, we need to know what the volume of the sphere is. So what is the volume of the sphere? And of the sphere. So we need to know that. So we need to answer this question. And also, what is the percentage? Like Jonathan says here, yes, exactly. Yeah. Well, you say, well, it's not quite that pi that you're thinking of. Yeah, exactly, that pi. The first pi that you're thinking when you're going to eat it. Yeah. But anyway, yeah, you got it right. Okay, so let's see. What should we do? First of all, we need to know what the volume of the sphere is. And here we go. Remember, the volume is nothing else than just 4/3 pi r cubed. And pay attention, the volume here will be, let me write it again, so that you guys can see it. It's a function, so it's a function of r. So V of r will be 4/3 pi r cubed. Okay, great. So we have this formula. And now, you see, the radius is varying, so it's increased. So we want to see how the volume will change. All right, great. Since we want to know how the volume will change, let me take the derivative. So V prime of R will be what? Will be 4/3 times 3 pi r squared, which 3 will go away. And this guy will be what? It will be 4 pi r squared. Right? Okay, so now we know this, so we can write this as dV is 4 pi r squared, right? Times dr, right? We can write this in terms of the differential. And now let's see. You know that the radius r is 21. Let's not forget that. Look here, you have this information here. And also we know that dr, pay attention because it's increasing. You see the dr, the radius is increased by 1%. So along this information here will tell you that the variation of the radius, right, the change of the radius is increased by 1%. So basically, that change, which is measured by dr, will be nothing else. So this guy here is nothing else than just this guy here. So it's 0.01 times 21. And by just replacing everything, so we have 4 pi times 21 squared times 0.01 times 21. It will give you approximately, well, I'll leave it to you to do the algebra. It's already done. It's approximately this number here, right? All right. And now the percentage error, guess what? It will be what? It will be dV over V times 100. So we have this, right? So V, also let's keep in mind, I forgot to say that V is of the volume is by just replacing the radiuses. Since we know that the radius is 21, the volume will be nothing else by using the formula. The volume formula will be will give us this number here, right? And now the percentage error can be computed easily. So it's like I said, it's dV over V times 100, and guess what? It will give you this. So dV over V times 100, you just replace these two numbers here. You're gonna divide dV over V. So this guy over here over this guy times 100, and in the end, it will give you 3%. So that is the error of the measurement in the volume of the sphere, right? Let's see another question, a very similar one, but this time I'm just gonna look for let's say for a circle, and let's see. So a circle is measured to have a radius of 5 inches, but the measurement device is only accurate to within 3%. Find the relative error and the percentage error in area. So I want you to think of this problem. I want you to tell me some ideas. So like I said, today we'll do only applications. Yes, exactly. Yes, Sabrina, you're right. So let's see, let's identify. So we have a circle here. We also have a circle to have a radius of 5 inches. So R is 5. So let's keep that in mind. But also we know that the measurement device is only accurate within 3%. That's very important here. And we need to find the relative error and the percentage error in area. Okay, so now we know that the area, so we're going to write here A of R is pi R squared, right? So that's the area of the circle. Like I said, it's a function of R. And now, if we want to compute the derivative, A prime of R will be what? 2 pi R, right? Right? It's actually the length of the circle. And now, if we want to write so we have this here. And now if we want to write the differential, so dA will be 2 pi R, which, right, times dr. And now let's identify. We know that dr, this guy here, right, but the measuring, it's only accurate within 3%. Right? So basically, since it's accurate only within 3%, so this means that we will have that this guy is 0.3, so this guy times 5 times the radius. So this guy will be dr. And now once you multiply these two, it will give you this number here. It's approximately 4.7124 inches squared. And now we would like to measure the percentage error. So how would we do how to measure the percentage error? Well, you divide dA to A, right? And you can just multiply by 100. So let's do that. And also, let's keep in mind that the area of the circle with when the circle has radius of 5 inches is nothing else. So the area is pi r squared, like we said. So the area will be 25 pi, which is approximately this number here, 78. And now we have all this information. So we will divide 4.71 to 78.5398, and we're going to multiply this by 100. So the propagation, the percentage error, it will be nothing else than just like we said. So this is the formula. And now we're just going to plug in. And once we plug in those numbers and we do the computations, it will give us 6%. Right? So that's the percentage error. Okay, so this was a pretty straightforward one. Now let me veer towards something else. Let me ask you something. So how would we use differentials to estimate this number? So I would like you to estimate, in fact, I would like you to plug this on a calculator to tell me what this is equal to. You know that the square root of 4 is 2, right? So we know this. But now we would like to estimate the square root of 4.01. We would like to see maybe this is close to what? So you see, once you just tweak it a bit, modify it a bit, you add just a little bit to 4, the situation will get a little bit more complicated. But you can actually do it by hand. You don't need to use a calculator. But just out of curiosity, use a calculator to see what this is equal to. What does your calculator give you? Can you tell me? I'm curious. Let's see, Abdul says 2.0024. So let's put it here. So the calculator says that the square root of 4.01 is approximately, let's see, 2.002498. Okay, let's put it like this. Okay, so this is the number that the calculator says. And let's see how close we're going to be to the calculator. So how should we use differential? So what kind of functions should we estimate here? So we should take the square root, right? So we should estimate this function. We estimate the function y of x equals square root of x. Because at some point we need to evaluate who is y of 4.01. Okay, great. So we're going to take this function. Let's do so. As you can see it here, y equals the square root of x. And now guess what are we going to do? We're going to take the derivative of this guy. So keep in mind that the derivative, so let me write it here, y prime of x is what? Is 1 over 2 square root of x, right? That's the derivative. So dy will be 1 over 2 square root of x times dx, right? But now let's see. But here comes the thing, right? So dy is this guy. And now, just like we said, if x is 4, then y is the square root of 4. And the square root of 4 is 2. But now we're not interested in just computing the square root of 4. We're interested in modifying a bit. So, but I want to ask you something. You see, the square root of 4.01 is nothing other than just the square root of 4 plus 0.01. And by the way, I don't want you to tell me that, and I think I stressed this out at the first lecture, and I think I've said it even last semester, and I'm going to say it numerous times. The square root of 4 plus 0.1 is not the square root of 4 plus the square root of 0.1, right? In general, the square root of a plus b is not equal to the square root of a plus the square root of b. In other words, the function, the square root of x, is not additive. I want to make myself very, very clear here. And I want to stress this out. It's very, very important for you to know this. But now let's go back to our problem. We changed this a bit, right? Because we know that 4.01 is 4 plus 0.01. So once we change this by 0.001, we'll have the following. You see, we will have that x, if we change x by 0.01, right? I think it's 0.001. Oh, sorry, here it's 0.001. Here's 001. Okay. So if we change this by 0.01, then the differential evaluated at that will be, so this guy will be here, this guy is dx, right, as you can see it here. And now we're just going to plug in, and then we will go, the change will not influence that much, so it will be 0.0025. So at the end of the day, so y will change from 2 to 2.0025. So let's see, are we close to a calculator here? So what did the calculator say? So the calculator says this, and our estimates, so let me write, says that the square root of 4.01 is, let's see, 2.0025. You see, very close. They're very close to each other. So these guys are very close. See, the calculator it's almost there. Well, the calculator will be much more precise then, but we can also be much more precise, but we need some other tools to be more precise. So this is just using differentials, and just try to see by hand how we can estimate this. Do you have any questions regarding this example? That's pretty neat, right? All right, if there are no questions, then I assume you got this. Let me give you another one. How are we going to estimate this guy here? So look at it. So we want to use differentials. So let's use differentials, since we just learned about them, to estimate this number. So we want to estimate 3 times 2.95 squared plus 5 times 2.95 plus 7. Think about it. First, you need to identify a function here that you can work with. In fact, please do it by a calculator. I'm curious what the calculator says. Let's see, estimate by a calculator. And our estimates. So I want you to tell me, what does the calculator say? Yes, exactly. That's the fun. But first, before we go into that, tell me what does the calculator say? So it's 45.8557. Okay, so that's the calculator estimate. And now let's see, how close are we going to be to this, right? We would like to see that. Wait, it's 45. 47, yes. Yes, exactly, 47, that's what I thought. 47, okay. So we like to see, that's why sometimes it's good to see if we like to compare this with the calculator to see how close or how far we are. All right, well, like Jonathan said, we have this function here. So what is the function that we're using? This quadratic function. And keep in mind that this guy here is a function of x. So y of x is this. Do not forget that. All right, what's the derivative of this guy? Y prime of x is what? Can you tell me? In fact, since you had the Gateway 1 exam, tell me what's the derivative of this guy? Exactly 6x plus 5. But I would like others to answer, not just Jonathan. All right, so the derivative of this. And now if we compute the differentials, right? So we will have that dy is nothing else than just 6x plus 5 dx, right? And now we would like to see the change. So let's see. 2.95 is the closest integer, let's say, to this number is 3. So we would like to see what happens when x equals 3. So at x equals 3, we will have that y is 3 times 3 squared, right? We're just going to replace y of 3. So let me write it here. Y of 3 is 3 times 3 squared plus 5 times 3 plus 7, which will give us 49. So at x equals 3, we'll have this, so it's 49. And now the change, let's see, okay, here comes the question. How are we going to change x? Since we would like to estimate y of 2.95. So how are we going to change x? So keep in mind that we have this number here. Well, how are we going to change x? From x equals 3 to 2.95, how does x change? It will change by what? Exactly, by 0.05, 0.005 you mean? Ah, yeah, exactly, 0.05, correct, or 0.005. Okay, so if we change x by negatives, right, because it changes from 3 to 2.95, so it will be negative, right? Then we can compute dy, and we're just going to replace dx by this. So dx, so the change will be just replaced by this guy. So now we can compute this, and it will give us this number, negative 1.15. And now we started from y of when x equals 3 is 49. But now when we change this by just a little bit, we'll get this number here. So we're just going to have to, so y will change from 49 to 47.85. So let's see, our estimate 47.85. So let's see. You see, it's very accurate. Well, we didn't go to another decimal, but this time we just, they matched perfectly, which is great. Right? Okay. All right, now I'm going to move to something else. I would like to show you a method, how to approximate this better, because we just did approximation by hand. And I would like to show you a method which is very effective. In fact, nowadays, there are much more effective methods than this one, but this is the most classical one. and it's due to Newton. Well, it's usually called Newton-Raphson Method. And well, you will go more into depth about this method when you take, for those of you who want to go deeper in mathematics at some point, this will be relevant to when you take a numerical analysis course. All right, so this method, like I said, is called Newton-Raphson Method. And let's see what this is all about. So we consider a function f that is continuous on the closed interval ab and differentiable on open interval ab, right? And here comes the trick. And we need to pay attention here. If we evaluate the function f at the endpoints of the interval, well, in our case, the endpoints of the interval are a and b. So in other words, if we evaluate f of a and f of b, and not just that, once we evaluate these two and these two values differ in sign, then we know by the intermediate value property that f has at least one zero in AB, right? Remember? Let me remind you this. So f defined on AB is continuous. And let's see how we translate this guy here, that f of A and f of B differ in sign. So these will be translated in the following: f of A times f of B is right, less than zero, right, a product. Then there exists a number c in the interval AB, let's say, such that f of c is zero. So that's the intermediate value property. Oh, sorry about that. So that's the intermediate value property. And we've done these examples. We have used this. If you go back to the last continuity lecture, I think, or the last two lectures, we talked about this. And we said that we have used this to show that a certain algebraic equation has a solution in a given interval. Anyway, maybe I'll discuss this on Sunday more on the review session before the midterm exam. I'll remind you how we show that a certain equation has a solution. And anyway, okay, so we know this by the intermediate value property. All right, great. If you look at the graph, I have the function f of x, and I have 2 points, right? x1 and x2. Okay, and their values will, f of x1 and f of x2 will be on the graph. And not just that, will be at this point here, right? You look at them. Okay, so now we would like to see, this method is, we would like to see what happens when we have a zero, right? Because here, and we would like to estimate the function around the zero. So let's see. So suppose we estimate this zero at x equals x1, right? So we have a zero at x1, right? So suppose that, so f has a zero at x equals x1. Okay. And well, what is Newton's method all about? So Newton's method is based on the assumption that the graph of f and the tangent line, this is important. So the tangent line at the point on the graph of coordinates x and f of x, and this tangent line, both the graph of f and the tangent line both cross the x-axis at the same point, right? This is the tangent line here, right? And this is the graph here. But this is the graph of that, right? All right, since we have this, now we can do something. So this is a huge, it's our assumption that graph of f, if the tangent line both crosses x-axis at the same point, just like it is illustrated in the graph, right? Okay, so based on this assumption, we can do something, and that's what we will call the Newton-Raphson method. Now, okay, let's see the details. Well, we can. It's quite clear that we can calculate the x-intercept of this tangent line, right? It's very easy, and we can use it as a second and usually better estimate for the zero of f. Okay, great. So I have a zero. Let's say at x1. So the tangent line passes through the point of coordinates x1 and f of x1, and with the slope f prime of x1. And now, since we have all this information and we know how to write the equation of the tangent line in the slope slope form, right? And the equation of the tangent line is this guy here, right? This is the equation. Let me write it again. So the equation of the tangent line that passes through, that goes through the point of coordinates x1, f of x1. Right, this is the equation. So let me, so y equals f prime of x1 times x minus x1 plus f of x1. So as you know already. Great. Now let's plug in a y equals 0. So if y equals 0, and if we solve this for x, this will give us this equation. So we will have that x is x1 minus f of x1 over f prime of x1. And well, thus from the initial estimate, this is estimate here, sorry about that. For the initial estimate, x1, we obtain a new estimate, x2. So x2 will be x1 minus f of x1 over f prime of x1. And now we can keep going. We can keep repeat the process. So again, we can improve x2, and we calculate the third estimate. So we say that x3 is x2 minus f of x2 over f prime of x2. And we keep going like this. And then at the end of the day, you will get something like this. Let me write it. You'll get that xn plus 1 will be some kind of a recursion, which is xn minus f of xn over f prime of xn. So that's the recursion. Anyway, like I said, so this will be the n plus 1 estimate. Right? So that's what you have to know. So you start from x, which is x1 minus f of x1 over f prime of x1, and then you keep going. x2, you write it in terms of x1, then x3 in terms of x2, then x4 in terms of x3. And in more general, xn plus 1, you can write it as equal to xn minus f of x1 over f prime of xn. Anyway, I don't want to go too much into details because usually sequences are studied more that's why I don't want to dwell too much on this kind of material, because this implies that you need to know something about sequences, and unfortunately this is not covered until calculus 2. But I don't understand why they put this material. Usually this is not in a calculus 1 material. This Newton-Raphson estimate. Well, it is in the book, but people don't actually cover it in class. But anyway, I just want to cover it for the sake of completeness. All right, and now let me give you, well, like I said, in this method, we can compute this approximation, right? Just like I said, xn plus 1. So this guy is xn minus f of xn over f prime of xn. So each successive application is called iteration. And as you can see here, the slope is nothing else than just a derivative at xn. And here we have the point xn plus 1, right? So here we have the point of coordinates. So this will give me xn f of xn. So just like I said here previously, right? It's the same thing. So we can iterate. All right. Now, let's do this. Let's see an application. I'm dying to show you this application. It's a very nice application. Look. And I would like you to look at this. So calculate 3 iterations, right? Only 3 iterations. Of the Newton-Raphson method to approximate the zeros of this function. Well, can you tell me what are the zeros of this function? Just by... So the first question we need to answer, what are the zeros of this function of f of x equals x squared minus 2? What are the zeros of this? Can you tell me? Plus minus what? You mean, what is that thing over there? You mean square root, right, Josh? That's what you mean? Okay. So yes, indeed. Square root of 2, for example, and also negative square root of 2. But one of them, let's say 1, 0, so answer is square root of 2. Or maybe we can approximate this 0 by using this method, Newton-Raphson method. We can approximate, this is nothing else than just an approximation of the square root of 2. So we'll see how close this will get to square root of 2. All right, so let's see. First, let's compute the derivative. So the derivative of this guy, f prime of x, is nothing else than just 2x, right? It's 2x minus 2 prime, but 2 prime is 0, so it's 2x minus 0, which is 2x, right? Okay, great. And now let's put x1 to be 1 as the initial guess. And also, let's not forget, okay, that the Newton-Raphson method says that, so says that we have this recursion here. Okay, so this is because we're going to use this method, right? Right, it's here. And this guy will be nothing else than just xn minus xn squared minus 2 over 2xn, right? Because the derivative is, so f prime of xn is nothing else than just 2xn. Okay, great. And now let's say that x1 is 1. That would be the initial guess, Right, let's start with 1. Okay, since we start from 1, x2 will be what? Well, x2, if we want to write it here, is x1 minus f of x1 over f prime of x1. And once we do this, look at x2. So keep in mind that we have this objective. So we need to approximate square root of 2 in some way. Right? So keep that in mind. So x2 will be nothing else than just 1 minus 1 squared minus 2 over 2 times 1, right? because f of x1, we just need to evaluate. So let me write it here. So f of x1 and f prime of x1. So f of x1 is what? Well, f of x1, you see, x1 is 1, so it's an f of 1, which is what? Is -1, right? And f prime of x1, which is f prime of 1, and if we write this here, so it's 2, right? And you can see them here. This is f of x1, and this guy is f prime of x1. So again, x2, by just doing some algebra, will give you 3/2. Okay, beautiful. And we keep going now. Let's go with another one. Oh my, this is a computation, so we're just going to look at it. Well, it's a bit computational. So x3 will be x2 minus f of x2 time over f prime of x2, right? So let's write that. Right, so let me write that, where should I write it? Here. Okay, let me write here, x3 is x2 minus f of x2 over f prime of x2. And again, by just computing f of x2 and f prime of x2, right? So basically f of 3/2 and f prime of 3/2, so we're just going to replace them there. So you'll get this. So it's going to be 3/2 minus fraction, and on the top we have 3/2 half squared minus 2 over, and on the bottom we have 2 times 3/2, right? Because that's the derivative. And anyway, by just doing algebra here, and I'm just gonna, we will get something. So it will be this. So you see, we started from here, which is 3/2, right? Which is 1.6 something, and then we end up with this guy, which is 1.1465. Okay. All right, great. And we can keep going. Let's go with another one. As you can see now, if we compute another iterate, right? X4 will be 17/12 minus, and then we're going to replace this here. So X4, let me write it here, is nothing else than just X3 minus f prime of X3 over f of X3, right? But X3, we know that is here, right? So we just replace this, and then we just keep going, and then at some point we'll get this number, which is approximately this. Well, as you can see, if you put it into a calculator, square root of 2, it will be very, very close to this number, 1.4142, 1569. Wow. You see how effective this approximating method, this Newton-Raphson is? So it's very, very close to square root of 2. No, I will not put this into a midterm. Maybe in the final, but anyway, we'll see. But I'll try to avoid this kind of material. I think it's, you need to know something about sequences. It's kind of you need to know how sequences behave. But anyway, I have to cover it because it's in the schedule. Okay. I think I'm going to stop here. Ladies and gentlemen, this sums up the entire material from the first 3 chapters. So we covered functions and graphs, we covered limits and continuity, and we covered more quantitative properties of differentiable functions, so derivatives. We will have 2 more chapters, and the next chapter will be talking more in depth about derivatives. And like I said, the material will get much more complicated from now on. So I would like you to, revise everything, do a recap of everything we have done so far, because if you don't know the material up to this point, you'll be in big trouble from now on. So I'd like to say that. Also, I'd like to say, I'll send you some information about the midterm exam. But just roughly speaking, the midterm exam will consist of 5 questions. There'll be proof-based questions. You'll have to write details, not just answers. You have to provide the proof of some things, or how to compute some things in detail, in great detail. I'll make sure that I will look at the details. And this is how I'm going to penalize you. I'm going to look at the details. I want to see if you wrote, if you know how to solve a problem, you know how to think of a problem. You know how they say, the devil is in the details. So that's going to be me when grading your midterm exam. Anyway, wait for my email. This will come probably on Sunday evening after the midterm exam, after the review session. So keep in mind that we have to do yes, I'll also send you more information about the review session, but also the review session, just let me say one thing, and let me say it again. The review session will be this Sunday from 6 to 8 p.m. So keep that in mind. 6 to 8 p.m., there will be a link. I will create a Zoom link, and this will be provided to you via email. You click on that link, and that's it. And I would suggest you attend the review session. It's in your benefit. Also, like I said, I'm willing to award extra credit for it to the final grade, right? I said, I don't know, how much did I say? Like 3% or something each review session. So there's plenty of opportunities for extra credit in this class. So please take advantage of it. Some of you don't take advantage of the extra credit that I'm awarding for attending the lectures, but anyway. So I think that's pretty much it. If you have any questions? Look at this guy. He's like, wow, there are 4 of them in a car. Anyway. When is the midterm? Well, that's a very good question. So the midterm will be available on my webpage at midnight Sunday, and you will have 48 hours to complete it. So it will be available at 12:00 a.m. Sunday night or Monday morning if you want, and you'll have to submit it back to me, and you'll receive precise instructions on how to do that. You have to submit it back to me on Tuesday, 11:59 p.m. sharp. I will not accept any late tests. So you have 48 hours. I think there's plenty of time for 5 questions. Each question is worth 6%. So.
I just wanted to clarify. The
yes.
session is on the 21st. Is that right? The Sunday.
Say that again?
The review session is Sunday the 21st?
Yes, Sunday, yes, it's the 21st, correct. From 6 to 8 p.m. I'm sorry, I'm taking of your time on Sunday. I apologize for that. Because, but the thing is that's the only possibility to, that as many students as possible will attend the review session. Otherwise, if I put it during the weekday, they'll be like, I have to work on Monday, on Tuesday, and so on. So, and based on my experience so far, that was the only time where I could get as many students as possible. Yes, of course, the lectures will still continue. Yeah, correct. We have lectures, correct. So we do have lectures. So the midterm exam, that's why I'm giving you like 48 hours, because you'll have plenty of time to cover it, to do it. Okay, if there are no other questions, ladies and gentlemen, I will stop here and we'll meet again on Sunday, but also we'll meet on Monday. So stay tuned, stay safe, and is it due? No, yes. I sent you an email with the homework, with the due dates yesterday, last night. Did you get my email? So first homework is due on the 19th, then the second one on the 20th, and then 21st, something like this. So it was a one-day incremental. Yes, I'll send all the details in an email today. Okay, guys, thank you very much, and I'll see you on Sunday. So wait for my email today. Let's see, the second gateway. Once we finish, it will be close to just before the final exam. So the first gateway, it's close to the midterm exam. The second gateway will be close to the final exam because it will involve integration. But anyway, there's plenty of time to go to second gateway. We'll get there at some point. Okay, I'll see you. Take care. Bye-bye.